we can start now. So are you ready? Hello?
Yes. Yes. Can you hear me?
Yeah, yes. Thank you.
Great.
Work perfect. So can I have all your attention? The Wentao Law is going to present us his talk on weak lengthening and cosmology. Please.
Thanks. Thanks, Professor Xue. Thank you, everyone.
You are from Nanjing University or where? Sorry, you present yourself.
Yes, thanks. Good morning, everyone. Thank you. It's my pleasure to give a talk on my research field. I'm Wentao Luo from University of Science and Technology of China. And my topic today is about weak gravitational lensing and cosmology. And firstly, I would like to start with the concept of dark matter. The concept of dark matter was firstly proposed by Professor Fritz Zwicky from the observation of velocity dispersion of the Coma cluster galaxies. And what he found is that the mass of those galaxies cannot hold such a large velocity dispersion of those galaxies, Coma cluster galaxies, which is as much as 1,000 kilometers per second. And so he came up with there must be some unseen matter to provide as a huge gravitational potential to hold such a velocity dispersion. And another evidence is from the galaxy rotation curve observed by Professor Vera Rubin. And what she found is that at larger scale, the rotational curve is not declining as expected, but flattened or even sometimes the rotation speed is a little bit higher. And so at that time, there are competing theories proposed by the Israeli scientist Professor Milgrom in the 1980s, which he called the modified Newtonian dynamics, aka MOND. However, as the more and more observational evidence come to play, and most of the evidence pointing to the concept of dark matter, to support the concept of dark matter. And for example, there's a CMB observation from Planck, and here shows the TT power spectrum of the Planck data, in which you can fit only half a dozen of the cosmological parameters. And with one of the parameter describes the dark matter fraction, which is about 30% of our universe. And there's astonishing observational results. And combining weak lensing observation and X-ray observation of the bullet cluster in 2016 and 2005. And the pinkish color shows the distribution of the hot gas from X-ray based on the free streaming of the hot plasma from the clusters. And the bluish the color shows the distribution of dark matter mass inferred by weak gravitational lensing from Chloe et al. 2006, based on the Hubble high resolution observations, imaging survey. And the astonishing fact here is that you can clearly tell the huge difference between the two different, the baryonic hot gas distributions and the dark matter distributions. And here, what do you suppose that in the MOND scenario, the so-called apparent dark matter should somehow follow the baryonic distributions. But here, you can see the distribution is very different from each other. And here, weak gravitational lensing plays a critical role to support this, the existence of dark matter. So what is weak gravitational lensing? What is gravitational lensing as a whole? Is there a strong gravitational lensing? Here is the, I will introduce briefly some concept of the gravitational lensing basics. So according to Einstein's general relativity, the light rays from distant galaxies has been bent by the intervening structures between the observer and this distant galaxy. And as a result, what we observe is the distorted image, like multiple images or giant arcs of those galaxies. And this kind of phenomenon is called gravitational lensing. And according to the distortion, the strength of the distortion, we classify gravitational lensing as a strong lensing and weak lensing.
Hello, we cannot hear you.
Oh, can you hear me?
Now, yes.
Okay, sorry. Okay. So according to the strength of the distortion, it can be classified as a strong lensing, where the distance between the gravitational center and the source is close enough in terms of the projected distance. And as the source goes further away from the potential center, and the distortion gets weaker and weaker. And so we call it a weak gravitational lensing. And the signal, it becomes so weak, it's only as weak as a percent level. And the dominant shape of each galaxy is the intrinsic shape of galaxy themselves. And here an example of a strong lensing case observed by the Hubble deep field imaging. And as you can see, it's not a photoshopped image, but it's a real observations of a strong lensing case. And the two yellowish eyes are the intervening structures, intervening galaxies surrounding by massive dark matter clumps. We call it a dark matter halo. And then the massive dark matter halos distorts the background star forming galaxy and form this kind of a face, the shape of a face. And so again, the strong lensing is very, the distortion is strong and it's easy to be identified. And so you can analyze the dark matter distribution based on strong lensing case by case. But for the weak lensing, as I said, it's as weak as only percent level, and also the dominance factor of the galaxy shape is its intrinsic shape, like it's elliptical galaxy or a spiral galaxy, it's disky or blah, blah, blah. And again, the dominant shape, it's a galaxy itself. But you can infer the distortion in a statistical way. So assuming that the blue point is the potential center of dark matter halo, follow some density profile like a singular isothermal, or so the famous NFW named after the three scientists, Navarro, Carlos Frank, and Simon White. And so the mean ellipticity is decreasing as a function of a projected radius away from the center of the gravitational gravitational center. So what you expect is, in a statistical way, is that the mean ellipticity is decreasing, follow some kind of a profile pattern. So again, here I would like you to remember that strong lensing case you can analyze case by case, and for the weak lensing you can only do it in a statistical way. You need the more background galaxy you have, the more statistical power you obtain. So again, for weak lensing study, you need a lot of background galaxies to do the statistical analysis. Okay. And basically, this shows a simplified cartoon that for the weak lensing studies, the geometry is simple. There's three factors like observer, the lens, and also the source. And compared to the distance between the observer and the source, and the size of the clusters, even the massive clusters, can be compared to a lens, can be considered as a plane. So we use a thin disk approximation to derive this so-called lens equation. So beta here is the position before the lensing effect, and the theta is the imaging position. And the difference between the lens and also the imaging the source and the imaging is called the deflection angle. So the deflection angle contains the information of the intervening potential. So the Jacobian between the lens plane and imaging plane, as I said, contains the information of the second derivative of the potential, the lensing potentials. And as a result, what we observe is a magnified source and also slightly distorted. And kappa here denotes the effect of magnification. It's a scalar, which basically enlarge the area of the background sources isotropically. And also the gamma 1 and the gamma 2 are the two distortion along different directions. But between them, their angle is about 45 degrees. It's a spin 2 quantity. And in order to connect the observational galaxy shape to these lensing signals, and Kaiser et al. In 2095 and developed this so-called the second moment statistics and built these ellipticity estimators. So this basically means if two identical galaxies, but rotated with 90 degrees, they will have the same amount of ellipticity, absolute value, but negative sign. So if the mean ellipticity, therefore, of those two galaxies goes to 0. And here, if we extend this assumption to an isotropic distribution of the galaxies, if there is no such a weak lensing signal, and we will have a distribution of galaxy shapes with a mean value of 0. Any residual can either from systematics or from the gravitational lensing signals. Okay. Again, we need a lot of galaxies to do the statistic to pin down the statistical errors. Hello, I hear maybe some people have some questions.
No, there's some noise. Gabriel?
Oh,
okay, you can keep going.
I see, thanks. So,
Gabriel, where is this noise come from? Is our part or his part?
I don't.
Please go on to see why
yes.
your speaker noise.
We can hear very well. Therefore,
yeah.
you can keep going. We have excellent connection.
Okay. I see, thanks. So again, I think Gregory is talking.
Gabriele, dove venne questo numero? You keep going, okay? Going slowly, okay. And I will give you enough time.
Okay, thanks. So again, in general, for weak lensing study, we need a reliable catalog. And so we built our weak lensing shape catalog based on a Sloan Digital Sky Survey in 2017. And here's the result of weak lensing signals compared to the previous work from Rachel Mandelbaum, 2005. And after we have this reliable catalog, and we can extend our study to other sciences. And for one example, that from our work in 2021 is to constrain the emergent gravity that developed by a Dutch scientist from Eric Verlinder, emergent gravity. In that scenario, give me a galaxy with a certain mass, and they will create some kind of apparent magnitude through some emergent gravity framework, which I don't know in detail because it's too theoretical. I'm an observer apparently. But in that case, no matter what the galaxy looks like, either it's a blue galaxy or red galaxy, you need to have exactly the same dark matter profile, which is not the case. So what we found is that even though those blue galaxies and the red galaxies, they have identical stellar mass, and their dark matter halo profile from weak lensing measurements differs from each other. So we put a very strong constraint on the emergent gravity. So anyway, with this shape catalog, you can do a lot of science like cosmology, measure the dark matter halo mass of the clusters, and then you can constrain gravity theory. It's like the shape catalog is like a trunk of the tree, and the science looks like the fruits based on this trunk. But also trunk needs roots. The roots are the data processing. So again, weak lensing is powerful, and a lot of ongoing surveys and finished surveys, they all consider weak gravitational lensing as their major project, like a CFHT, based on the 3.8 meter telescope at the top of Mauna Kea, and also the dark energy survey based on the 4 meter telescope in Chile, and also the Subaru 8.2 meter telescope, also at Mauna Kea. This is the telescope I've been working on for more than 3 years. I'm still working on this telescope, the data of this telescope, and also a Vera Rubin telescope, which will start to observe, hopefully, in 2 years. Also, all of them consider weak gravitational lensing as their key project. And however, as I said, the signals either from gravitational lensing or systematics. And the systematics are the ones that we don't want, because it really messed up with the science that we want to know. And one of the most important systematic is point spread function. And it's basically the combination of this optical design and also the atmospheric seeing, especially for the ground-based telescope. And as a result, for a star, which should be a point source, and what we observe is an extended, blurred, extended source. And that's not the final case. The detector we are using is called a coupled charged device, aka CCD, and it's a pixelized detector. So for example, a galaxy looks like this, and finally what we observe in reality is only a bunch of pixelized images over the detection limits. So again, weak lensing, we need a reliable catalog, and the reliable catalog are rooted in the reliable data processing and the systematic correction and stuff. And once we have the catalog, we can do a beautiful science. It's just like a tree. And so here, I call it weak lensing tree. Again, from the root, we need to estimate the point spread function at the position of galaxy where we don't have stars. And also we need to remove these systematics from the point spread function, and we estimate the shape for each galaxy. And also we need to perform simulations to calibrate the hidden systematics according to the different observation conditions. And also photometric redshift also are necessary. And then these are the basic factors to build a reliable shear catalog. And once, again, we have the shear catalog, we can do galaxy formation, constraint cosmology, and measure the cluster mass, and also galaxy lensing stuff. Basically, I call it weak lensing tree. And then here comes to the major contents of the gravitational lensing, and I will control my time, but let's see. The first part, I would like to briefly introduce the Subaru HSC SSP survey, the year 3 shape catalog. This is should be the trunk of a lot of major science. And the second, based on year 1 shape catalog, we have also done some science, like we study the dark matter halo around active galactic nuclei galaxies. And we want to know if those active galactic nuclei locates in a specific, if they prefer some environments, like some specific dark matter halos with certain masses. And also the second one is the 2x2 point correlation function constraints on cosmology. And for the third part, I would like to introduce the 2.5 meter wide field survey telescope that built by University of Science and Technology of China and Purple Mountain Observatory, and which also consider galaxy formation and cosmology weak lensing as one of the key science. And again, I will conclude with this weak lensing structure, the tree structure. So here shows the survey region of HSC SSP, the final region. So it contains 3 layers: the wide layer, the deep layer, and ultra deep layer. And the weak lensing shape catalog is based on the wide layers. So remember that this is going to be the final survey region. So it's a still ongoing process. And it contains 5 broadband photometry measurements, and with the R band magnitude down to 26 magnitude at 5 sigma detection for point sources. And the deep region covers 27 degree, and the ultra deep region covers 3.5 square degree, with extra 4 narrow bands. And also the coverage specifically selected to overlap with other surveys like Gamma, KISS, XMM, LSS, to maximize the multi-messenger science. And so far, we have the 3rd data release, which is released in August last year. And here shows the coverage of the first year autumn field. And the upper panel shows the coverage of the autumn field from the data release 1. And the lower panel shows the data release 3. As you can tell that from data release 3, we almost accomplish most of the regions, except for some shallow colored regions that we need multiple multi-epoch observations afterwards. And again, we divide these regions into sub-regions, which overlaps with the VVDS, Gamma survey, wide 12H, and the hectomap. And all in all, it covers about 433 square degrees, which is basically more than 3 times larger than the year 1 ship catalog regions, and which improves the signal to noise by a factor of square root of 3, roughly estimation. And also because during the observation time, and there are a lot of unexpected disasters, natural disasters, like the seismic movements, volcano eruption events, and also as well as the weather. And as a result, the final area cannot reach up to 14,000 square degree. But anyhow, we try to maximize the survey region because a weak lensing needs a lot of the larger the area, the better, and the analysis, the signal to noise. And so as a result, we change from 6 dither to 5 dither, meaning that from the same observational region and the previous before the disaster, and the same region we observed 6 times, and we co-add these 6 images together to reach up to a depth that deeper than each exposure. And now we move to 5 dither. That is, for the same region, we only take the exposure 5 times. And this only affect like a 0.1 magnitude difference, which will not affect the total analysis for weak lensing, because we do the source cut, the magnitude cut at I band 24.5, and whereas the depth of I band can reach up to 26. And here the different color shows basically the 6 dither region and also 5 dither region. So, and as tested, this 5 dither and the 5 dither and the 6 dither pattern does not affect that much the PSF reconstruction, the systematic control, as we show in the paper. And we do test the point spread function size, the reconstruction. One of the important things for the weak lensing is the size, the reconstructed PSF, because at each position of galaxy, we don't expect we have star. If there's a star with a galaxy, and then this galaxy suffers from blending issues. And so what we do is to reconstruct, to infer the PSF at the position of galaxy by sampling the stars around near the galaxies. And so the y-axis shows basically the reconstructed size minus the PSF, the star size, and over, this is basically the residual of the reconstructed size. The gray region denotes the requirements for this the year 3 survey. And we did do some cut, like if those regions have a PSF reconstruction worse than this 0.1%, and we'll discard those regions. And this is basically the data quality control to make sure that your catalog is reliable enough. Okay. I only said weak lensing, and weak lensing also have a lot of subfield, and one of the subfield is called galaxy lensing. The physical interpretation of galaxy lensing is that you take a lens galaxy, you take a foreground galaxy between the observer and also the background galaxy, and thinking that it centered at the potential center of its dark matter halo, right? And then you select the background galaxies and measure the shape and do the stacking and extract the tangential shear signal, which is caused by these foreground galaxies. And the critical density is basically the geometry factor in this lensing system. Okay, so the physical interpretation is basically the cross correlation between the galaxy and matter. Okay, what we measure is basically given a galaxy and also the matter, the dark matter correlation. Okay, and here's one of our work to study the galaxies with different properties and see if they have the same halo mass. And this paper has been published from A&A. Basically, as you can tell, we split the galaxies into AGNs, active galactic nuclei, host active galactic nuclei, and star-forming galaxies, and also quenched galaxies. And what we found is that the stellar mass to halo mass relation between the AGNs and star-forming galaxies, they look like similar. They look similar. And somehow the quenched galaxies, they have a higher halo mass. They reside in a higher halo mass in this, even though their stellar mass are similar. So this is also the one that we used to test the emergent gravity scenario. And again, we further want to explore what's happening with the active galactic nuclei, host galaxies. Why they locate they prefer in a lower dark matter halos. And so we have we generate an AGN sample from the WISE and also HSC. And then we create a control sample also from HSC and specifically targeting the study and see how different the AGN halo and normal galaxy halos. I will skip this and also, and here's one of the major results, because for the normal galaxies, we have a lot of galaxies because AGN as a whole only occupies only 10% of the galaxy populations. And here we divide the galaxies into 6 stellar mass bins, and the data points are the weak cleansing signals from around the AGNs, which basically tells you how massive the dark matter halo around these active galactic nuclei. And also active galactic nuclei usually caused by the supermassive black holes. And also if we have reliable black hole measurements of each AGN, so we can actually skip the stellar mass part, we can directly build the connection between the supermassive black hole and the halo mass. So that is also the project we want to proceed with for the next step. Because from SDSS survey, we have already had beautiful catalogs from Liu et al. 2019, as well as Shen et al. From UIUC 2011, with AGN, with supermassive black hole measurements inferred from the broadline emission lines, like magnesium 2 or C4 or H beta, H alpha. Anyway, all in all, in this work, we only focusing on the stellar mass to halo mass relation of those AGNs. And here is the most important result. What we observe is that for the control galaxy, for the normal galaxies, and if we divide into high stellar mass and the low stellar mass, and what you observe is that the density profile from the measured from a weak cleansing is much higher than the high mass AGNs. That basically means that you cannot tell the difference of those halo mass from the high stellar mass sample and the low stellar mass sample of AGNs. And here's the modeling part of these normal galaxies, which I will skip. Basically tells you that our model is not reliable enough. And also we built the stellar mass to halo mass relation. The horizontal axis is the stellar mass from the normal galaxy sample and also from the AGN sample. And the y-axis is the halo mass inferred from a weak gravitational lensing. And here, specifically galaxy-galaxy lensing. And as you can tell, the normal galaxies more or less follows the stellar mass to halo mass relation from Alexei Liuto's work, previous work, from high redshift and low redshift. The high redshift empirical prediction is the blue line, and the orange line is the low redshift ones. However, the AGN sample as a whole locate right at the knee of this relation, where the star forming efficiency is the highest. But when you split into high stellar mass and the low stellar mass, and it seems that the halo mass doesn't change that much as normal galaxies. Okay, that is what we found. That means AGN, active galactic nuclei hosts, they do have their preferential favorite halo mass. And also another study from Richard Mandelbaum et al. 2006, and they discovered that radio AGNs have higher halo mass than the radio quiet active galactic AGNs, which further complicates the interpretation of this AGN activity and its host galaxies, and also its dark matter halos. And so the project is going on, and stay tuned. But this paper has already been accepted for publication in APJ. And another work I've been involved with is combining the clustering and the galaxy-galaxy lensing to constrain the cosmology. And the clustering is basically the two-point statistics, two-point clustering measured from the BOSS data, the low Z sample, the one redshift bin low Z sample, and the two redshift bin from the CMAS sample. And also we measure the galaxy-galaxy lensing signals and put cosmology into play and try to constrain the sigma 8 and also the acid and omega m, etc. And here's the signals. The upper panel are the weak lensing measurements from the low Z CMAS and CMAS2, CMAS redshift bin 1 and the CMAS redshift bin 2. And the signal to noise are shown in each lower legend. And the lower panel as a whole are the projected correlation functions of the low Z sample and CMAS sample. And the graded region are the regions that we discard, we ignore, try at smaller scale, we try to avoid the baryonic effects. And at larger scale, that's basically our modeling part, which is based on the dark emulator. That is the maximum scale that we can model based on that HOD model. And here's the constraint power given this combining joint likelihood analysis. We recently, people always mention something like the tension between the Hubble constant, the tension from the Hubble constant from the strong lensing and also the supernova from the Planck Hubble parameter. But here in the weak lensing, we also have some tensions, like we call it lensing is low. That means the constraint of S8 parameter from DS and KISS and somehow is lower than the Planck data as shown in this figure. So for time's sake, I will briefly introduce the 2.5 meter wide field survey telescope built by USTC, which is the university I'm working on, and Purple Mountain Observatory. And this is the basic parameters of this telescope. And we also divide into 3 layers. The first layer, we call it wide field survey, which is roughly take 45% of all the survey region, including the time of opportunity. And also we have a deep high cadence U-band survey, and which can reach up to U-band 26 at 5 sigma detection for point sources, and which we will use more than 45% of all the observational time. Especially we want to apply the new moon, the plus and minus 7 days from the new moon for the U-band survey. And the deep high cadence survey is one of the very interesting region with the 16% overlap with HSC survey, but we can provide U-band survey and have a very deep U-band survey. So here, the deep high cadence field, the concept is not going too deep, but also it's very high cadence, all right? The high cadence is designed targeting multiple transient events like supernova, tidal disruption events, as well as the FRB, afterglow, and etc., etc. So this is our transient heavy survey. So usually the deep region is not very wide, but here our deep region is up to 1200 square degrees with a very high cadence. In order to differ, to distinguish our deep field to other deep field, so we add deep high cadence U-band survey. So this is basically the scheduler, and we want to use in the deep field, and we want to use the darker night for the U-band and G-band, because this U-band and G-band is very heavily affected by the moon phase and the moonlight. And whereas the other band, especially G-band, I-band and I-band are not that affected by the moon phase that much. So again, this wide field, and we want to maximize the science, the wide field is overlapping from the Northern Galactic Cap, is overlapping with SDSS, DESI, and EBOS, so that we can do the cross correlation of clustering and galaxy-galaxy lensing, like a 2-by-2 point correlation function, as I showed before just now. And we have a 4 broadband photometry combined EBOS spectroscopic data or the DESI data in future. And also the survey depths shown here, and which is similar to the DES survey in terms of the depth, so that the weak lensing study is going to be comparable to DES. And the deep high cadence survey, the 1200 square degree, as I said, with 17% overlap with HSCSSP and PSF, as well as Keys and Gamma. Okay. And the survey depth can reach up to 26 in U-band. Okay. So that is really comparable to LSST U-band. Anyway, LSST U-band is not a major science. So here we're targeting the U-band high cadence and deep U-band high cadence as our major legacy data. And for galaxy formation and cosmology, except for weak lensing shear catalog, and we can also apply the deep U-band, G-band, and R-band broadband depth to find about 10 to the 7th Lyman break galaxies, which is very valuable to select high redshift clusters and also for the future targeting selections. That's basically the brief introduction, and I will conclude using the galaxy lensing tree. The weak gravitational lensing study basically like tree. So the roots are the data analysis and the simulations, which you will not have great publications, but these are the crucial procedures are needed for weak lensing study. And then you have a shear catalog. And the shear catalog are the trunk to support all the beautiful science like cosmic shear and cosmology, testing the gravity, and also cosmology, etc., etc. Okay, all in all, in this talk, I introduced what is a weak gravitational lensing, and also the year 3 ship catalog I have been involved in from the HSC-SSP survey, and also the 2 science based on this weak lensing ship catalog. One is AGN galaxy lensing. You can study the halo of AGNs, as well as combining the clustering and the weak lensing to constrain the cosmology. And also I briefly introduced the wide field 2.5 meter wide field survey telescope built by the University of Science and Technology of China and also Purple Mountain Observatory. And so it's going to have a wide survey region and a deep high cadence survey targeting not only transient, but also have a lot of legacy data that contributes a lot to the cosmology community. So I'll stop here and take questions. Thank you. Thank you all.
Thank you very much for a very nice talk. So now
Thanks.
we have time for questions. Please.
Wentao,
Yep.
your presentation was very remarkable, and the set of publications that you are preparing, we will study them with particular attention. But I would like to take this occasion to congratulate you on this USTC telescope in Purple Mountain Observatory, which looks to be really an instrument which set China in the wider and advanced field of lensing all over the world. Congratulations again. And what I am personally very interested is to understand better, we will study your paper, the correlation between the black hole in mass in the active galactic nuclei and the halo mass. And this is your recent paper, and we understand you will keep going in this direction, which in my opinion is really very, very important. Congratulations again, and we will keep in touch. And I'm sure that the other people, Piero Rosati especially, will be very interested, and the people in Ferrara in our joint doctorate. Maybe
Thank you, Professor Ruffini.
we have
Thank
some
you. Thanks.
student of yours to come with us and collaborate in their PhD, and we will be ready to collaborate on the theory.
Thank you, Professor Ruffini. And I really appreciate your comments. And I personally met you in USTC in the year of 2000 some time, and also in Shanghai. But I know you at that time, you didn't know me. I respect you a lot. And your gravitational book has been translated into Chinese by Professor Shouping Xiang. And I also have a very strong collaboration with the team from Italy, like Nicola Napolitano and also Mario Radovic from Padova stuff. So thank you again. And I also hope that you can come to visit China, come to visit USTC. Thank you.
Well, USTC is inside ICRA. We are having some problem, but I am confident we will solve them soon, and to have more strong collaboration, even within ICRA of USTC.
Yes, thanks. Thank you a lot. Thank you very much.
I have a question. Sorry, I didn't follow the early part of your talk. I mean, the goal of the optical telescope from the USTC, what is the goal for detect which source, which type of gamma ray burst focus on, or other source?
So
the goal of this telescope, yes, from USD, which source dedicated to observe the.
So
You understand what I mean?
yes. So the design, the major science of this telescope. Recently, we just had a scientific evaluation assessment by a group of scientists from different institutes of China, and so finally we divided into core science and also key science. The core science are targeting to find various transient events like a supernova, a different kind of a supernova, the tidal disruption events, and also we want to do the follow-up observations of the kilonova, neutron-neutron star merger, or the neutron star and black hole merger that with optical signals.
Yeah.
And also for the multi-messenger, we're also targeting if we can observe the GRB afterglow, optical afterglows, as well as other transient, like F-dot.
As I know, in the GRB afterglow detected by some other optical telescope, only reached to the 22 magnitude, cannot be reached to 26. The 26 is more sensitive telescope, really required to more sensitive.
Thank you, but I'm not very optimistic about this observation, because 26 is the co-added image. It's not like one exposure we can reach up to the 26 magnitude. It's a co-added image. In that case, we can reach up to the co-added image. Is like you have longer exposure. For example, if we have each exposure 10 seconds, and we have 10 exposures, that means we have roughly we can take it as 100-second exposure time. So the 26 is not for one exposure.
Okay, yeah, good.
Yeah, and for the key science, where we have galaxy formation and cosmology, weak gravitational lensing, and the selection of Lyman brick galaxies at very high redshift, and also the near Earth objects, etc., etc. So weak cleansing is also one of the key projects, but not the core science.
Okay, thank you.
Of course. Yeah, thank you so much.
And just a moment, Can you hear me?
Yes, yes.
Yes.
Wentao, well, of course, thank you for your talk, but let me mention we have this week, we are presenting a very, very fundamental work which has just been accepted in APJ by our team, and has to do with a new approach to the first example of application explicit of binary-driven hypernova for GRB. And the leading person is Wang Yu, which will be present next week. Is recovering, unfortunately, fortunately is recovering from this terrible sickness, but I'm sure it will be ready for next week. And I invite all of you to follow this, because it's a new era in which for GRBs, which were traditionally conceived as single object with ultra-relativistic jet and so forth, is the first example of a binary-driven hypernova in all details and explaining the new science related to this object. APJ asked us to make a special press release of this very important work. And, Wang Yu will, I hope, if the thing progresses day by day, we'll be ready next week to present the data and the results.
Wow. Congratulations, bravo.
Okay, all my best.
Thank you.
Okay,
Yeah,
good.
I will follow the events.
Yes.
We have a couple questions in queue, please.
Yes, I would like, hello, thank you for this very nice talk, Wentao. I'm very interested in your relation that you show about AGN and a host galaxy halo from your weak lengthening prediction. The former one, I guess. The one is a couple of, yes, this one. So have you checked with the, you know that there is a Ferrarese relation between the central mass, black hole mass and sigma dispersion velocity of bulge, but then there is another correlation relating the black hole mass and halo host mass. Of course, this relation has an spread, an intrinsic spread due to the different sources, but I don't know if you have checked with this correlation your results.
That's a very good question. Your question basically describes what we want to do next. And so here, the sample, we don't have reliable black hole mass measurements because, you see the number of those AGNs we select here contains 8,882, but only 1,000-ish with the spectroscopic from the SDSS region. So in that case, we cannot measure the reliable signal to noise, weak cleansing signal. So, but based on the new data, like the year 3 data, we can measure a very high signal to noise. I have already got the signal, and we divide it into different supermassive black hole bins. But I cannot show here because I need the permission from the group. Sorry.
Okay, thank you. Thank you. Okay, thanks a lot.
Now, next question. Okay, I suppose you are going to ask something. Okay.
Thank you. Yes, I want to ask about how the weak lensing analysis can help in the estimate of the Hubble constant.
What is all? I have some questions.
Oh, okay. No, I mentioned the Hubble constant just to emphasize that there's not only the Hubble tensions, there are also the tension, we call it the sigma 8 tensions, where the weak lensing sigma 8 measurement is always lower than the Planck, but it's still roughly in two sigma away. So in the future, if we have more data, we either think it comes from systematic, or it's really a tension from some kind of underlying physics that we don't know. But at this stage, we don't have enough sample, or we don't have enough signal to noise to tell the truth, because it's only 2 sigma away from Planck, as you can tell. But also different surveys have different degeneracy, different estimators have different degeneracy directions. And also we need to explore various kind of potential systematics, like the photometric redshift and the calibration of a bias, and also the correction for the point spread function, etc., etc. And so here again, as I said, the weak lensing tension, the reason that I bring up the Hubble tension is because Hubble tension is so significant. It's almost more than 5 sigma between the supernova, the Pantheon project, away from the Planck Hubble constant. But if whether the weak lensing, whether the weak lensing is tension or not, we still need new data to confirm, or either confirm or rule out this kind of tension in future. Yeah.
Clear. Thank you.
Can I say something, okay? Or you please, okay.
No, I'm fine. Thank you.
Okay, so I think I'm happy to see, to hear that what you say, though you are not completely sure. You say the sigma shear, the sigma 8, is lower than the Planck value. Is what you say, right?
Yes.
Okay, yes. Very good. I think this in my mind, this has to be glorious qualitatively. So then I ask another question. What about the omega m? The value of omega m that you get estimate, okay, low, maybe in 2 sigma or whatever, is lower or is up larger than Planck?
That's a really good question. But the weak lensing constraining power of sigma 8 and omega m is weaker because, as you
weaker
can tell,
again. Good. No, weaker. You say
no,
it's weaker than Planck value?
No. From Planck, Planck has a very tight constraints. What I mean is that weak lensing, the constraining power is weaker, not only because the data quality, but also because there's a strong degeneracy between the two parameters, sigma 8 and omega m. Okay? So that is why S8 is actually the combination of sigma 8 and omega m. So which we want to ignore the degeneracy of this sigma 8. So sorry for not clarifying this parameter for the time's sake, but S8 is the combination of sigma 8 times a square root of omega m divided by 0.3-ish. In that case, we can ignore the degeneracy between the sigma 8 and omega m. As you can tell, this green line, the degeneracy of omega m and sigma 8. And so S8 doesn't have this kind of a strong degeneracy between these two parameters. And so weak lensing now, they try to only focusing on the constraint of S8, this parameter. So the reason we show omega m and sigma 8 is just to tell people that you see there's degeneracy between these two parameters.
Okay, as far as I remember, the sigma 8 shear, okay, shear of the matter, the sigma 8, the S8, there's by their definition, there's a square root of the omega m amount. But anyhow, what I try to say is, you say, okay, the sigma 8, okay, or S8, okay, forget, because now we are not going precisely. Sigma 8 is, the value is below is smaller than the Planck value. This somehow, as I feel from the intuition of physics, somehow indicate also omega Okay, leave alone this definition S8 sigma 8 for its own right. But that means omega m value should be from lengthening, should be also smaller than the Planck one. Because there's a very reason is if you sigma 8 is sigma 8 is below the Planck measurement, and this C is a sort of the correlation between the matter. So let's indicate the matter should be also smaller than the value indicated in the Planck measurement, which is in the CMB area. Yeah, okay. And here, the length in your measurement, the redshift, how much it is? About 1?
0.75.
0.7, exactly,
That's
0.7 or 0.7 less than 1 slightly. So the
Yes.
Planck one is measured in a very large left shift, and this means something. Omega m is different in where you are measuring the gravitational lengthening is different from where the CMB is.
Yes. So for that, I would like to, can you see my screen now? The Zhang et al. 2018. So
Yes.
due to this kind of tension between Planck and weak lensing, so people have already developed some theory, like in a phenomenological way. For example, there's one case, if you modify some equations, like tell people that the dark matter in the during the history of our universe, the dark matter evolves to become dark energy. So there is some kind of a
Exactly.
rate of
This
exchange.
is what okay, so you
Exchange.
Good. Okay.
Exchange.
It's
And so there is a paper. Yes, and also Marco Boldi has some kind of simulations based on that. And also we do our own simulation to mimic this kind of simulation. And there is one model that the dark matter flows to dark energy. And it can perfectly explain why the sigma 8 from the weak lensing is lower than getting smaller. And without changing other stuff. But here what we found, if you constrain the parameter you constrain by combining the keys data, such a low sigma 8 and omega m, and then your universe are going to have a much less massive halos. As a result, your predicted weak lensing signal with the same abundance will be shown like the red line. But whereas from the real universe, what we observe from SDSS based on this weak lensing shape catalog is the data points, the black data points. And also, as we also simulate a fiducial lambda CDM, and which is consistent with the real measurements here with the observations. That tells us, even though if you try to just to explain this sigma is low issue, and just by adjusting some phenomenological model, you need also to consider the smaller scale weak lensing signals. So that paper is published in 2018 PRD, and tell people that if your exchange rate between dark matter and dark energy is too, aggressive, that means it's possible it's going to be ruled out by the weak lensing observations.
Good. In the other word, it's weak lensing measurement, or what you call, will provide another evidence for cosmology.
Exactly.
Yes.
Very good. This is exactly telling us something in CMB. The matter is much, not much. The matter at the CMB evolved to the redshift about 1. some matter is going to lose to the dark energy. Very clear signal.
Oh, really?
Yes. Means that the matter getting smaller, that's why your sigma is getting smaller. This is what my intuition tell me.
I see. I see. But not that much, but not as much as
but now that's accurate. Let's pin down the things. But at this direction, this is what I see the direction. How evolve from the Planck in CMB and to the weak lensing in the redshift by 1.
I see.
Wentao, well, we are very grateful for your time and presentations. And I would like to urge you to be active in the collaboration within ICRA and ICRANet. From USDC, we have an agreement signed. We have all the activities going on. We just need to exchange more students. And of course, invite you to visit us in Pescara. And we have next week the meeting still going on. And I hope that as many people as possible at USDC will participate, because we will have both Liang Li and Wang Yu to present some very, very exciting new result. Liang Li especially will present something very interesting, that is how the spectra and observation of GRB changes with Z. And to us was extremely surprising, because now we are seeing that the GRB nearby, zeta equal 1, has 7 different characteristic features. But the number of features decreases with distance. And this is something very interesting. It's like that GRB are becoming too faint for fundamental science. But the very exciting point is that what we have learned from GRB at small z can be now used in understanding active galactic nuclei. And therefore, we can use this experience to translate to active galactic nuclei. This is the reason we are so interested in your work, and keep going up to z equal 10 with the active galactic nuclei, where we cannot go on with GRB. This is something very, very, very fundamental, and we would like to increase the collaboration with USDC in this direction. Okay.
I see. Great, thanks. Yes, great. Thanks for your invitation. That would be my honor to join this fantastic collaboration. And personally speaking, for GRB, I have tried to measure the GRB dark matter halo using weak lensing, but failed because most of them are at higher redshift. So you have a smaller number of sources to do the stacking statistical analysis. So, but I think in future, we can definitely not only study the difference from the spectrum, like Liang is doing, and also I think we can also study the dark matter profile using different multiple weak lensing surveys. Thanks a lot. That's and I will actively join this meeting during the next several days.
Let me stress the key point once more. GRB can work up to z equal 1 and learn fundamental physics. If they were not GRB, we could not have understood the fundamental physics of black holes. And therefore, we could not afford to look at active galactic nuclei, because we do not know in active galactic nuclei how to make the fundamental theory. Instead, we have developed the fundamental theory in GRB, and we can apply now to the equal tenets of ordinary galactic nuclei, we have the key to understand. This, I think, is the most exciting part of our commitment. Hope to have your strong participation. Remo.
I see. Thank you, Professor Ruffini, and thanks for your comments. That is really my honor to join this fantastic collaboration. Thanks.
Bye.
So very good. We are glad to have your presentation in this morning. And if is there any more questions? I give you the one chance more. If not, let's thank the speaker, Lo, again. And we
thank you. I'll stop sharing here. Thank you all.
Thank you. So we are, the next speaker will be Long, but I don't see he's in connection yet. So we are waiting for Long in connections.
Francesco Longo.
Sì.
Francesco, sei in orbita? If not, we have coffee break up to 12:15, and we start again at 12:15.
Yeah, and how about this Mimosa?
Mimosa, I don't know if she's connected.
No, I don't see.
Okay, I think let's have the coffee break. We deserve that after this very beautiful presentation.
Okay.
Of
okay, so we will rejoin in 10 minutes.
No, 12:15.
In 12 o'clock. Okay, so that's okay. 20 minutes.
12:15. 12:15. As in the program.
But the long will be the, let me see the program.
12:15, 13. At least.
So Francesco Long will be in 12:15. Okay. Hello. Francesco Longo, yeah, you're online.
Yes, I am here, yes.
Very good. So I guess
sono anch'io qua.
Now we have a speaker, Francesco online, and we will restart our meeting. So Francesco, can you share your screen?
Yes, I will immediately. So I share the entire screen so that, let's say, any other problems of sharing the things will not happen. So let me start showing the presentation right now. So thanks for the possibility of being here to this very nice summer school. And let's say together with Professor Ansoldi, who could not join because he's on travel, we decided to have this presentation like more an introduction to what will happen next week when more experienced theoretician, more than me, I mean, I am an experimentalist, will discuss about some of the implications of these big discoveries. So what I have, let's say, thought about this presentation was, as it is in the title, so gamma ray burst at high and very high energies, a path to success. Why I decided to have this title? Because as you will see in my small presentation for today, I will discuss about how this very new window that has been recently, where recently I mean the past 10 years or so, have been opened, let's say, really required quite a lot of, let's say, inventions, quite a lot of activities, quite a lot of really experimental clues that were decided before these discoveries were made. So this is the message that I want to convey you. So here already in the first picture, you can stop whenever you want. I have many slides. I don't know if I will can to cover all of them, but in case I will show the most important one. Let's say what it is really important is this picture, that this kind of discoveries, in this case, this the famous GRB 130427A, they were so important that in some cases they warranted even the cover of this important magazine named Science. But before starting, these are for us in Fermi, they are very sad period, because 2 days ago, a friend of us that you know, because he came, I think, to some of our presentation, I think that he was one of the speakers also in France when we had the meeting on thermal emission from gamma ray burst with Felix Ryder. And this guy, Magnus Axelsson, a dear friend of us, suddenly passed away 2 days ago. This was really something that we could not anticipate. So I think that, let's say, this is the first moment that I can speak publicly, and I want to remember him because this was a tragic news, and he was such a kind person. He helped quite a lot in the preparation of the second GRB catalog that I will discuss later on, and I would like to remember him in this talk. So he passed away a few days ago. So after remembering Magnus, let me go ahead with the presentation. So what I will present will be very brief, since I don't know whether there were other presentations about GRBs before me. Surely there will be many after me, as I said, by other experimentalists and other theorists. And remembering what Lorenzo Amati several times presented, he presented that the GRB history could have passed 6 eras, but I think that nowadays they are 7. So I adapted his presentation, adding 1 era that I will discuss in a moment. Then this year is the 25th anniversary of the discovery of the afterglow. So it is something that we shall remember as well. This will be, I will be very brief, because then I will go immediately into the main topic, which is the high energy emission from gamma ray burst and the very high energy emission from gamma ray burst. Since these two are strictly related both to the prompt phase and the afterglow phase of this phenomenon, it is quite important we have a broad overview in the beginning. So the 7 eras that I adapted this presentation from, really one from Lorenzo, let's say, followed basically the main discovery. So after the first period, which was called dark with the question marks, because it was not really dark, many, let's say, discoveries and also many theories were put forward in that period, followed the discovery in 1973 by the Vela satellites. Then during the Batze era, Batze-on-Bond-Compton, the main discovery was the spatial distribution. It was the first hint toward the cosmological origin of this phenomenon. Then, what I said before, so 25 years ago, the discovery of the afterglows by the POSAC satellite, and the following discovery of the optical transient associated to the GRBs as well, that led indeed to the final confirmation that the GRB are indeed placed at cosmological distances. During the 4th era, that let's say here Lorenzo, let's say, created quite a, let's say, a small era in a very small period due to the observation of this small satellite that first confirmed the origin of light or long burst. This was discovered by Sachs, as you remember, in 1998, sorry, with 1998-04-25 GRB. But this 030329 was one of the first, let's say, confirmation that long bursts are associated with supernova. I see Massimo Della Valle might comment later better than me. Then the fifth era is the one which is still ongoing, that is named after the Neil Gehr's Swift Observatory observations on the very early afterglows, the discovery of the short GRB afterglow, and the question mark on the usage of GRB for cosmology based on the previous relations, but still questions are rising from this topic, but the new windows are opened. We can stay here for months discovering or discussing about these topics. But also in the Swift era, several other classes of GRB came out, and let's say the discussion that probably the Professor Ruffini will make next week will be, let's say, highlighting the different classes of GRBs. Last but not least, nowadays we are living in the sixth era of GRB, the one named after Fermi discoveries, or Fermi Agile, as I will argue later on, which is somehow related to the confirmation and the full exploration of the high energy emission component from gamma ray burst that was not completely known or discussed before. And also, of course, much recently, the confirmation of the origin of short gamma ray burst associated with the neutron star mergers. And I added to these 7 eras, to these 6 eras, the 7th one, which I call the very high energy era, that started in 2019, when both Magic and Hess, let's say, claimed or announced the discovery of the very high energy emission from gamma ray burst, which was also let's say, a long-awaited discovery, as I will show you later on. So the gamma ray burst, as you all know, they are a typical phenomenon. They are characterized by these 3 characteristics, which are not related to each other. So a very spiky temporal behavior, quite a smooth spectral shape without no particular ingredients, no lines, whatever, just 2 power laws smoothly connected, and the spatial distribution homogeneous and isotropic, sorry, not homogeneous, isotropic in the sky. Then the GRB phenomenon in the Batze era, where let's say, this first dichotomy was discovered, that GRB appeared, apart from these characteristics, which are, let's say, cannot be organized in an easy way, the only dichotomy that was found in that period was the division between short and long gamma ray burst. Short are the one which total duration is less than 2 seconds, and long are the ones that are that last longer than 2 seconds. And they are characterized not only by a different duration, but also a different hardness ratio with the different flux in the 2 bands of Batze. So these that appeared just quite a phenomenological distinction, nowadays we know that they are pointing to different progenitors. So these in the Batze era led to the great debate, 1995, where these 2 distinguished scientists discussed whether the GRB were cosmological or galactic. That time was not yet known. And Sir Martin Rees concluded that we needed a new type of observation. And this came, as I said, 25 years ago with the discovery of the afterglow by the Beppo-Sachs satellites, thanks to the possibility of having on board both a gamma ray instrument, the gamma ray burst monitor, and an X-ray instrument, the wide field camera, that detected the prompt emission, so the one that lasted hundreds of seconds, similar to what I presented just to now. And they had the possibility to repoint the satellite and discover the long-lasting X-ray fading emission, which is called the afterglow. That was also awaited theoretically, but was not discovered up to then. And the discovery of the afterglow led to the possibility of pointing optical telescope, radio telescope, and nowadays we live in this afterglow era, where these information are crucial to the determination of the distance of the GRB, the environment of the GRB, somehow also the classification of the different afterglows, and so on. So nowadays, no one else is still working just on the prompt phase, but we need the information of the afterglow. The afterglow is let's say, the following phase that follows the first initial and very bright observation named the prompt. So nowadays, as I see, I have covered just practically half of what I want to tell you, but I have still half an hour because I will go more into the detail on this high energy and very high energy emission from gamma ray burst without any theoretical interpretation, as I claimed since the beginning, that I will try to argue that the high energy emission can still be due both to the initial part of the emission, so during the so-called prompt phase, but also and most probably in the afterglow phase, while sorry, the very high energy emission is much more linked to the afterglow phase due to observational constraints so far. So let's go then into these new eras, so the Agile Fermi Era, and so with the discovery or the confirmation of the high energy emission from gamma ray burst. I will be very fast in highlighting the past observation, and I will discuss in detail some of the observations made by these two satellites. So this emission indeed was not discovered by Agile or Fermi, but it was discovered again by an instrument on board of the Compton Gamma Ray Observatory named ICRANet. ICRANet made several discoveries, among those the emission of high energy from gamma ray burst at energies greater than 30 MeV, which is nice because it included in its observation several phenomena that were not yet understandable in that period when they were obtained. So, for example, in 17th of February 1994, so last century, there was something here, for example, that a burst that lasted hundreds of seconds, observed in X-ray, in GV, or 30 maybe 100 or maybe, lasted 1000 seconds, so 20 minutes or so, and then after, let's say, 1 hour and a half, the burst was still there with a photon of, let's say, almost 20 GeV coming 5000 seconds after the burst. This was a mystery. At that time, 1994, the afterglow were not yet discovered. So these raised quite a lot of questions. How it is possible that the burst is still active so quite such a long time after the event? The same was true for this one. This was a short journey. You see that in Bats it lasted just 2 seconds. But you see that the photons of ICRANet came also afterwards. They arrived up to 8 seconds. And most importantly, I remember that because I studied these phenomena since 1996 or so. We were all thinking that in this very short period that was dominated by the dead time of the instrument on ICRANet, there have been many more photons here in the prompt phase due to this, let's say, dead time. So we expected quite a lot of photons in the prompt phase. Last but not least, let's say there were many interpretations of the broadband spectra, and some of the theorists predicted this just synchrotron emission that was putting together all the data from the different experiments on board the Compton. This was called the shock synchrotron model by Marco Tavani in 1996 and 1998. Because most of the GRBs did not show any evidence of external spectral components, but a few one, like this one that was again in 1994, showed a persistent component in the calorimeter of ICRANet that lasted longer than the, let's say, the prompt phase. So this was again a question raised during the ICRANet era. So which were the ICRANet heritage on gamma ray burst that Agile and Fermi, as I said, in a long path to success, had to explore? First, is there any extended emission? How is common in GRB? Is there any high energy emission during the prompt phase, or it is just in the longer standing phase, which was not yet called afterglow because we didn't know about that yet? Which are the spectral components? It is just synchrotron emission, or it is we need other components? And much important, is the high energy emission ubiquitous, or it is just in specific gamma ray burst? So for that, we needed optical timing and broadband fast detectors. So this took quite a lot. And finally, we created, or we built first the Agile that flew in 2007. So we are 15 years old. And then Fermi, which flew on 2008, that explored, among other topics, also the gamma ray burst. So let's see first Agile and gamma ray burst. Agile, as you all know, or you might know, is an Italian space agency mission that was built just by Italian Institute and Industries, led by INAF and INFM people. So Agile is the most compact payload for energy astrophysics. It has an extra instrument. It has a small calorimeter aiming to get gamma ray burst in the prompt KV band, but it has a gamma ray imager based on silicon detectors that aims at detecting gamma rays from 30 MeV to 30 GeV. So Agile is, let's say, is made of several instruments. Let me not go into detail, but just highlighting the X-ray instrument and the gamma ray silicon tracker, which I will now discuss more in detail. And then last but not least, again, there is calorimeter that is also used for gamma ray burst detection in the proper their proper energy bands. So let me skip this slide because it is not important. So the mini calorimeter of Agile, let's say, published two catalogs in the energy range that is typical for gamma ray burst of 300 kV up to few tenths of MeV. But what is new, that is the high energy emission, are the observation by the other instrument, the tracker. So the first gamma ray burst that we observed was observed 1 year, practically 1 year after the launch. So it is something that we didn't expect. We expected much more many gamma ray bursts. So we had to wait quite a year before getting the first one. And you see immediately that this is the mini calorimeter, so 300 kV, 350 kV. You see the typical spiky light curves. But you see that this is the high energy emission. And you see that during the prompt phase, even though Agile had the trigger dedicated to small times, no high energy photons arrived during the prompt, but there were other photons later. And to our surprise, the prompt was not bright as we expected. So you see that most of the GRB come after the 66% of them come after the prompt phase. So these also confirmed that practically we didn't need any other spectral component, and the grid fluence for this burst was on the afterglow, on the for the continuation of the spectrum of the prompt. So no other extra component was needed. But we learned quite immediately that let's say the GRB are different one each other, and indeed 1 year after, this very famous and very interesting GRB was detected by Agile, which is called 090510, for which indeed there was a very strong spectral variation, because the high energy emission was detected just once the prompt was over. And it lasted much longer than the prompt. This is again a short GRB. And you see that it lasted up to 10 seconds, while the prompt phase is just less than 0.2 seconds. And more important, it has a completely different spectra shape, like let's say it was a power law with cutoff in the prompt phase, and in the delayed emission is a power law without cutoffs. So gamma ray bursts in high energy are very much different to what we expected. Last but not least, Agile detected a handful of GRB, but let's say 10 years ago already, let's say quite a long time ago, we did a study. At that time, we detected just 4 GRBs. I highlighted just the first two, so 08, 0514 and 09, 0510. But you see here that the fluence of the GRB, so how much energy they emit in the typical energy, is quite similar to many other GRBs, for which we could put upper limits which are at the same level or even below the flux that they observe. So that means that the high energy emission is not a common property of high energy of GRB, but it is something that is peculiar to some of them. And this is something that the theorists are trying to explain, as Remo probably will discuss next week. So Agile GRBs, I will not read all of these, but they were among the brightest GRBs. We see around 10 events per year, so 1 per month, basically together, Agile and Fermi, I mean. They have some single spectrum or some other additional spectral components. They are characterized, I hadn't the time to show, but high Lorentz factors. So now let's look into Fermi, because I have, let's say, to go also the very high energy emission. So Fermi, LAT, instead is, let's say, a bigger instrument with respect to Agile. It is 16 times larger and much more a calorimeter with much more deeper radiation lengths. That allows to go up to more than 300 GeV. And it has a gamma ray burst monitor that is standing from 8 kV to 40 MeV. And the key characteristic of LAT was that it has let's say, very huge field of view, and it is surveying the sky in surveying mode, while the GBM observes the whole unocculted sky at any time. So why it is important that the LAT has this quite large field of view and that this sky survey? Because this was designed, as you see, it is very much similar to Agile with the silicon strip tracker, cesium iodide calorimeter, an anti-coincidence detector. So you immediately see that here there is no X-ray detector, and the calorimeter is not used as a GRB detector because we have the GBM on board. So this discussion, this strategy was made because having the two instruments on board, we could cover on the typical prompt GRB spectrum quite, let's say, quite 7 or 8 energy decades. So the GBM covering the peak of the spectrum, and the LAT extending to very high energies. So we have the possibility of observing the prompt phase with a very large energy band. This was unexpected till then, because also Agile is not so able to measure the spectra since it has a very small calorimeter. So we, let's say, made several expectations. Are there spectral components? Do we see this increase in spectral shape? Are we able to measure, let's say, the variability, to measure spectral pseudo-redshift estimation? Are we able to measure time lags? So there were several expectations before Fermi was launched. And indeed, many of them were done, as I will show you later. I'm showing very old slides because I want to show you the path to success. All the things that Agile and Fermi made were actually planned in advance. So they were not just by chance discoveries. So first of all, LAT was designed to have a larger energy range, a better energy resolution, larger peak effective area, better angular resolution, larger field of view, and a smaller dead time with respect to ICRANet. Because in order to have, let's say, many more GRBs, we need a wide field of view, an efficient observing mode. We need to have more photons, so a low dead time and a large effective area. And also to have a very better, good GRB, very better or good GRB localization, having a better angular resolution and increased energy coverage. As I said, in the early phase, the one that also Agile had, we discovered 1 GRB per month. So the first one, the first important one, the first one was not very bright, but to our surprise, LAT detected one of the most farthest GRB that it detected. Nowadays we have another one which is at larger redshifts, but this one was the first year. It was in September 2008, and it was quite a bright GRB, and it was localized at Z4.2, so quite a large redshifts. But it is quite bright, as you see here in this plot. You see these are the light curves for GBM with, let's say, very smooth, apparently light curves with not so many peaks, so very dilated. The LAT peak is not coming during the prompt, but it is extending. It is not seen here, but in the following slide it will. It extends to larger time with respect to the prompt phase. And you see that we have some events here that these led afterwards to develop a new kind of event selections. So you see that what I said before, that the test statistics that it is used by the LAT team to quantify the possibility of the burst to be detected, extends up to 10 to the 3 seconds and much later, much more larger than the, let's say, the 10 or tens of seconds that the GRB lasted in the GBM band. So that means that the LAT emission is very large. The high energy emission is extended in time, is delayed. It starts later and extends much larger in time. Again, another example on single burst, and I will discuss about the general properties, 090510. 090510 was the short GRB that I already discussed, detected also by Agile, but LAT has such a huge effective area that could detect many more photons, and also these 31 GeV photons, for which, for example, we made some studies on quantum gravity possible time dilation effects, if this GRB was, this photon was associated with any of these peaks on the short GRBs, on the short GRB pulses. So let's go now to the catalogs. As I said, the first one was released using 3 years, where we detected 35 GRB in 3 years, so basically 1 per month, as I said, while the GBM detects 250 GRB per year, with half in the LAT field of view. That means that we have almost 360 GRB in 3 years, so that means that 1/10 are detected by the LAT. So this is the similar rate as I discussed while I was discussing about Agile first results. So during the first catalog, in the first 3 years, we apparently found that the GRB are the brightest one with respect to the huge population, but with some hints that they might go to even to lower fluxes. And last but not least, it appeared in the first time that there were a class of hyper-energetic GRB, like 08, 09, 16C, and other two that I not discussed, or 09, 05, 10. Then, important point is that the spectral shape is different. So this is the beta index, the spectral shape, the characterization of the spectral shape in the GBM band, which is around -2.9, which is typical of the band spectrum. And instead, the LAT emission in the extended emission is pointing to -2. Quite all the GRB. So that also pointed to a different origin of the high energy emission. Then after the first catalog came this monster burst, the one that for which I started the presentation, 130427A. This one, you see that here I highlighted, this is 1,000 times more bright than 0916C, not because it is brighter in itself, but it is closer, maybe. This one is Z4, is much closer. And of course, this one also was we were able to, let's say, study the arrival time of the high energy photons. And you see that there are some of these photons that are not compatible with some theory explanation of synchrotron emission in the expanding shells in the external afterglow model. So this was the first time for which some other mechanisms were required to explain these high energy photons. So LAT apparently didn't detect any claim of inverse Compton, nor in this one. So there was no a clear indication of another spectral component in this one, like the one that ICRANet made, but this was an indication that some other components were needed. So, of course, I showed the first catalog, but we improved our analysis. I will not go into the detail, using a new reconstruction of the events that allowed us to get new photons, even higher energies from 08 to 09, 14C, and also searching with a larger area with respect to the GBM error boxes. So we found more GRBs. As also, this one is a path to success because we developed quite a long of tools to get, let's say, you see that in the first catalog we have 28, but using the new algorithm in the same period we have 45 GRB, so quite a larger number. So these let's say, arrived to the fact that the first detection rate was, let's say, 10 GRB per year. Nowadays, we have 15. So it is somehow new GRB physics, maybe not, but probably the high energy emission is related to the late time emission. One important key point that I will like to discuss that is also included in the catalog later on is somehow an analysis that we made that if we divide the luminosity of the LAT by the ISO emitted by the GBM, all the GRBs, this was an observation that Gabriele Ghiselini made first, but we made the same analysis with Lara Nava, and all of them, short and long, they align to the same line. So this also points to a common origin. So the second catalog, and this is why also I started remembering Magnus, because Magnus was one of the contators of this very nice second catalog, contains 186 GRBs, so quite a larger number. They are lighted here. The blue are the long one, the red are the short ones. And you see that in this picture, that you have the GRB long and LAT long and short, and you see that they are going to much lower fluencies, much lower fluxes. Apparently, there is not any more the need of very high fluent GRBs to have the emission in LAT. So this first claim apparently is gone. What is not gone are some characteristics that I'll explain briefly, because I now want to spend the last 10 minutes on the very energy emission, is that the LAT first point starts generally after the first point 0.5 when the T90 of the GBM starts. And also the last photon detected by LAT arrives later than the end of the GBM. These are the line is the equal time. And quite important, this might be that LAT is just after the prompt. It is not true, because the first photon of the LAT arrives here sometimes, let's say, before the GBM time is over, or maybe during the GBM time, or these are the one for which we don't know because the GRB was outside of the field of view when it happened. And then thanks to the survey mode, we got to the location in due time. What is confirmed is that the high energy emission in the standard phase, the spectra shape of the LAT points to the e to the -2, while when we do the spectra analysis during the time when the GBM is still active, the spectra shape is much more softer. So that means that the LAT emission is comprised of both prompt and afterglow phases. So the conclusion for the high energy emission is that there are extended emission, extra long for in the case for 130427A, which lasted hours. So they are emission in the prompt phase. There are some extra components, multiple components. I didn't have the time to go into the details, all of that. And we have upper limits in several bursts, as I showed, showing my paper, but there are several others. Normally, I concluded this part with a question mark for the very high energy emission. This is not anymore true, because we know that we are living now in the very high energy era when the very high energy emission from gamma ray burst was discovered. So there are two types of detectors. The first one are the Cherenkov detectors that detect the light emitted by the particles in the electromagnetic showers generated by the very high energy gamma rays. And there is the extensive shower that might detect photons coming from the, let's say, they might detect photons, measuring the particles themselves. I mentioned that not because they detected any GRB so far, but because they might be the only or the best instruments to detect the prompt phase of GRB in the very high energy. So stay tuned in case some of them will detect any. So let me discuss about the path to success. First, let me discuss about MAGIC. MAGIC are two twins Cherenkov telescopes located in La Palma, Canary Island. They were designed to rapidly follow the GRB. The first one, when MAGIC was still a mono telescope, was in 2005, 050713A, where MAGIC pointed to that after 50 seconds. So you shall imagine tons of these of the telescope pointed immediately to the GRB in order to catch the high energy emission, but nothing was there. And you see the same picture as the one that I made, and these are just upper limits. Several other upper limits were made in other GRB together with LAT. These are, let's say, LAT upper limits. These are synchrotron and synchrotron self-Compton models. Apparently, nothing was there at very high energy emission. The same was done by Hess. Hess pointed to this telescope sometimes after the burst was declining. They could point just during the plateau phase, and they detected just upper limits, and then the burst faded away. You see that these are probably they were not in the night, so they pointed once they could, and they could not detect anything. The same was done by Veritas. Sorry, is located in Namibia. It had four 12 meters telescope. Nowadays they have a 28-meter telescope in between the array. Veritas instead is still an array of 12 meters telescopes located in Arizona, and they pointed to the 130427A, the monster GRB that I showed. Unfortunately, it exploded during moonlight, so they had to wait the day after. But also in the day after, they placed interesting upper limits that were, let's say, constraining in a certain way models for the synchrotron Compton model of the extension of the LAT spectra shape. So apparently it was a nightmare, because you arrived early in time, day after, or just in time, hundreds of seconds after the burst, and you detected anything. So with great surprise, because we had to wait 15 years, so from 2004, when MAGIC started this search, that MAGIC detected for the first time, the gamma ray burst 190114C, thanks to these two, maybe if Razmik Mirzoyan discussed this topic yesterday, he already said that, because this detection was thanks to some improvement in the MAGIC team itself. So the possibility of analyzing partial moon data and the possibility of analyzing large zenith angle data. So these were, apart from the rapid movement, these were two key ingredients in detecting this GRB. So you see that the GRB was pointed after 50 seconds, so after 30 seconds that the alert was received, but after 50 seconds the GRB started, detected by a BAT, and you see that it detected a decline phase. Also in this case, the GRB was not, I'll correct, these are the DOI, so sorry, the box is not properly covering. You see that here the events are much at larger energies and much more, and let's say incompatible with the just synchrotron model. So these really claimed to the need of another spectral component. This is true what was done, analyzing all this data, LAT, BAT, XRT, and others. And our colleagues, namely mostly Lara Nava, developed this model for which for the first time was needed to have this extra component that fits together the XRT, GBM, LAT, and MAGIC data together with the absorption by the ABL and the internal pair attenuation. So this was the first time that some, let's say, inverse Compton component was detected. The same was true by Hess. Apparently, they detected the GRB, evidently, so not apparently, evidently they detected GRB 1 year before us, so 180720b, but it was announced and published in the same Nature issue. This was very interesting, detected 10 hours after the GRB. They do not point because it was during the day, probably. They pointed the night after, and they detected the GRB 10 hours later in the deep afterglow phase, which is also interesting because this is a different phase with respect to the other one. So it is not something that is somehow similar to what MAGIC did. MAGIC detected at this period here. This is, let's say, another phase of the GRBs. This is now I'm saying that we are in a different phase, in a different era, because we have to understand how common these detections are. Indeed, these two detections were so important that Nature dedicated to them a news and views written by Bin Zhang, and they claimed to have the need for the synchrotron plus synchrotron Compton models. After that nice, let's say, endeavor, in the same year, 2019, which will be remembered as the TV high energy emission year, has detected another one, which is much closer indeed. It is 190829A. This is the attenuation by the extragalactic background light. And you see that these are at much larger redshift, 0.4 for 190114C and 0.6 for 180720B. This is much closer to us. So you see that its emission can extend up to very high energy without being attenuated. And indeed has detected 3 times during the first night, then in the second night, and even in the third night. So this is really astonishing. This burst is really, really interesting. So they, in the paper, even there is some, let's say, discussion in the community. In the 1908-29A, they claim that if you relax somehow the requirements on the high energy emission from synchrotron, you can still get a better explanation of the spectra shape, while with the self-synchrotron Compton, apparently the spectrum is not very well fitted. There are other authors that claim the difference, so the discussion is still ongoing. But I am presenting here just the result of the collaborations. So how to solve this issue? I think that this issue, just 1 minute, this issue will be solved by the new generation Cherenkov telescope array, which is named the CTA, which has rapid slewing, will go down to energies down to 20 GeV in order to catch as many GRB as possible. And it will have 3 types of telescopes. The first one prototype is already built in La Palma. It is called LST. It is 23 meters. We have 2 types of MSTs, 12 meters, and small telescopes, SSTs. And we will build this kind of array in 2 sites, in the northern hemisphere, in the southern hemisphere, with the different types and number of telescopes. But what is important is that the CTAO in the northern array, so the one which will contain the LSTs in the first point, you see that with respect to Fermi, that detected the prompt emission, as I tried to argue before, in these energies where also CTAO will be sensitive, is 10 to the 4 times more sensitive. So if, in this case, luck will help us, the GRB will be triggered during the night, we will be able to repoint within hundreds of seconds, which is currently really feasible given the structure. So we just need to have the GRB exploding during the night and without a strong moon. We will be able to catch the prompt phase, which is still the holy grail of the very high energy emission. But we are prepared, and the path to success has been tracked. You see that, for example, Ulises Barres, also a friend of this group, made in COSPAR 2 years ago. So you see that if we catch the alert, this will go to the immediate repointing, and with the 30-second latency, the real-time analysis will let the external observatory see if an emission has been detected by CTAO on a transient scale. So we hope to catch soon the prompt emission from very high energy GRBs. So let me conclude just in time with one minute delay. So the high energy satellites shedded almost light into the emission mechanism for gamma ray burst. The prompt seemed more soft, as I showed in the LAT catalog. There are some upper limits in the prompt phase. Not all the GRB are emitted in the prompt phase. The afterglow is more feasible for the energy emission because of its temporal decay and its prolonged emission. And we were able to get the detection of the very high energy counterparts of gamma ray burst in the afterglow phase, mostly, as I showed, and we don't know yet whether there is any component of the very high energy emission in the prompt. And this will be the discovery which is just behind, let's say, in front of our schedule, So stay tuned for further and nice discoveries that might come in the years to come. So thanks for attending and listening.
Thank you very much for presentation. Very good. Now we have time for questions, or a couple questions.
Francesco, let me first thank you for this beautiful summary, but at the same time also to the perspective of new results. And really very nice. And we have to make an effort to explain to a larger community what really is going on, because all the models which were used up to now, they are practically overcome.
Mm-hmm.
And this is a very, very, very important moment to clarify this problem. And this is part of the reason which we organize next week. And we plan very much to keep discussing with you from our understanding.
Oh, this is why I said that one of the key points will be to understand the different classes as you made. So which are the GRB classes that are more, let's say, favorable to be detected at very high energy or high energy. And I remember the useful discussion that we had, for example, in the meeting in Rome a few years ago, and then these were indeed confirmed later on. So I will be very happy to participate during the discussions. I have exams in the university, so I'll try to be present whenever I could.
Absolutely. And but we need to collaborate also in explaining this situation.
Definitely, thanks, Raymond. Yes, for sure.
Because it's really a major effort, and we need your presence. And but let me tell you one of the high points which is surfacing finally, and very much depends on the one you being able to participate, because it's just coming out negative, fortunately. Oh, by the way, I would like to know what happened to this collaborator who died. What was due to COVID or not?
No, apparently not. We don't have many news because he died in Japan. He was spending some time in Japan. He had, let's say, a position in Sweden and another one in Japan. So apparently he was in Japan, so we don't have yet any more news.
I see.
Apparently he had an heart attack. This is what, let's say, we know, but no more than that.
Okay. Anyway, condolence. And anyway, next week, we are preparing the presentation of a paper which even the editor suggested to make a very clear press release, which we are trying still to work on in this house. And this is the first clear evidence of an alternative way from the traditional approach, speaking about a single source working at very high gamma and interacting with the interstellar medium and with the jet, ultra-relativistic, and so forth and so on. This is a counterexample, which to us is extremely important because it gives the first evidence of the binary nature of gamma ray burst. The need for a binary nature, the need, and to see where the binarity comes in, both in the prompt and in the afterglow, both. And this, I think we are going to prepare this, and I hope that Wang Yu will be sober enough to be well negative and being able to speak. But also we have something extremely new, which will be presented, I hope still, by Liang Li, which is extremely surprising. But certainly we will present the first one in full detail, and maybe also the second one. And of course, we are also teaming with, in this house, with Massimo Della Valle to understand better the deep nature of the supernova. What is really the supernova? What is what is the role of the supernova? It's just an interesting fact, or there is so much deeper in the role of the supernova. They look to be standard. Yes, they are standard, but they are standard in systems which are completely different. This is incredible. I mean, supernova standard, we have shown this, but they work on sources of 10 to the 54, 10 to the 52, 10 to the 49. How can it be? What is the role of these objects? It's just, they're just there by accident, or they're telling us something fundamental in these sources. Therefore, these are the three topics I would like to share with you and with everybody else. And please send around the notice as many people as possible to listen and participate. Well, for the moment, I thank you a lot. And since it's time for lunch, we have to break absolutely. And thank you again, and see you next week.
And see you to all friends, and stay in touch. I like very much this meeting, so keep me in the loop.
I have a short question.
Yes, please.
First of all, thank you. It was very informative and nice talk. About correlation of the LAT observation and the XRT observation, did I miss something, or did you mention something in your talk?
No. The LAT are not correlated with the XRT.
Okay.
The XRT, the late time emission in the TV time is correlated with the decay phase of the X-ray. Let me show again one slide.
Because this is very important.
Yes. I show you both the S1 and the magic one, so that you see that it is similar to in the both GRBs. So let me share again, so that I have also corrected the box of the reference, so that you will see that. So you see that here the magic data are going down. Yes. And the XRT curves are going down as well, in the same, with the similar, similar shape, similar slope. The same is true with Hess. Also, Hess is this point here, and the XRT is declining. Unfortunately, in this burst, they could detect only 1 point because it was a late time. But the new one, this one, you see that here they have the XRT light curve in blue, and the red one is the TV. Also, in this case, the two, let's say, decay time are somehow parallel.
Yes.
Okay. It's very good. This is a topic we will discuss next week.
Yes. Okay.
But I think it's extremely important. There is something new. There is something new, and I already insist on this point. There is something new about TeV radiation. We should be attentive enough to catch the novelty. It's not just extrapolation, it's something new. And we see that exactly in these two cases. But there are other cases. There are other cases, for example, in all the damp data, there is a lot of TeV radiation. Therefore, there is something basic new about TeV radiation. And it's something which we should not miss, which is dual to the electron, but not to the electron. Therefore, in my opinion, there is something much more fundamental in particle physics. And I'm trying to convince our chairman today to write up immediately a paper on this topic, because I think there is something much more profound than just GRB physics, and very likely particle physics. I insist, Sheshen, to work hard on writing up the paper you are preparing. We are preparing. Thank you.
Thanks.
Okay.
Okay, thanks, Francesco. Thanks to all the speakers this morning. For all the nice presentation. So we close the section, this morning section. And I would like to say, unfortunately, we have not fixed this technical problem for video presentation of Professor Rafalski. So this afternoon, we won't have any more speaker. Thank you, everybody, speaker and participants.
Bye. Bye-bye. Ciao.
Ciao.
This afternoon, we will have Jon Rafalski at around 3 o'clock or later.
No, the video has not been fixed. Problem.
Okay, then we will.
Maybe when they are repair this problem technically.
Okay.
Maybe we'll present some slot in next week.
Yes, thank you.
Okay.
Bye-bye. Ciao.
Bye-bye.
Ciao.
Bye-bye, everybody.